Hey everyone, so today we're going to talk about the second derivative test, which is a really nice, possibly faster way to find local extrema, aka relative max and min, and just another way of finding critical numbers. So we want to, first of all, review what does the first derivative test mean. And by the way, the second derivative test, there's only a couple scenarios where you have to use this. Okay, so we'll actually do one later on, but second derivative test in a general sense is a nice tool. You don't have to use it necessarily. There's usually, 80 to 90% of the time you can use the first derivative test. But there are a couple scenarios where you have to use a second derivative test. And it's also just a quick way, if it's the right type of problem, to find relative maxes and mins. So to refresh your mind, what is the first derivative test? Okay, this is how you typically found local max and min. Okay, number one, you would find the critical numbers. Critical numbers are, remember, when f prime is equal to 0 or when f prime doesn't exist. Okay, then you would make a sign chart for f prime, right? You would kind of do like f prime, put in the critical numbers, put in the endpoints. Okay, and then step 3, you would determine maxes or mins, relative maxes or mins, by analyzing this sign chart, right? So you'd look like, oh, it changes from positive to negative, therefore it's a relative max. Okay, so that's the first derivative test, just as a heads up when I refer to that. And that's something you can still use pretty much, like I said, on every problem that's looking for relative extrema, except there are going to be like a couple scenarios where we need this second derivative test, hence why we're doing it. And it's a nice way, like I said, possibly faster at times to use it. So here are the conditions for finding local max and local min for second derivative test. All right. So if, first of all, f prime, we'll talk about this point c. So if f prime of c is 0 and f double prime of c is positive, okay, aka concave up, right? Okay, so if we have f prime of c is 0, there's a horizontal tangent here, and we know that this function is concave up, okay, then a local minimum occurs at x equals c. All right, so that's really a quick way to figure this out if there's a local min. So again, there's two conditions. Okay, we just wrote them above. Two conditions. Number one, f prime of c is 0. Number two, the second derivative is positive. We don't really care what the value is, just if it's positive or not. aka it's concave up, so it has this shape with a 0 slope at the bottom. That guarantees, okay, a local min. Some people get confused here, be careful. Positive goes with minimum. I know that sounds a little weird. The next one you can guess, when we're concave down, we have a maximum. So negative is going to go with maximum. So people get a little confused on that. So make sure you organize those two thoughts. Okay, so the second piece here, like I said, if f prime of c is 0, so we still know the first derivative is 0. That's still an important feature here. But we then know that f double prime of c is negative, aka concave down. Okay, if we figure out both of those pieces, then we can guarantee a local max occurs at x equals c. Okay, so again, this one has the same, not the same two conditions, but same idea of two conditions. Number one, f prime of c has to be 0, aka horizontal tangent on that original graph, or 0 slope. And if f double prime of c is negative, aka concave down, 0 slope, this guarantees, you can see it visually, this guarantees a local max. Okay, and again, make sure to note here, maximum is going with concave down. So visually it makes sense, but sometimes people get confused with positive and min and then negative and max. All right, so there's your obviously important info. The last thing I want to say about this is if f double prime of c is equal to 0 or it does not exist, right? So this, we were dealing with negative or positive. If it's 0, okay, then we can't even use the second derivative test. So we'll have to use the first derivative test. First derivative test, because the second derivative test tells us nothing. So let's try out a couple examples of this. All right, so first one, it says, use a second derivative test to try to classify any local extrema, relative maxes or mins of this function. If it doesn't say second derivative test, you could do whatever you want. You could do first derivative test or second derivative test. Okay, so we're going to try this though. So the first thing you want to do, we still want to get our first derivative. Okay, 4x cubed plus 8x plus 0. We want to set it equal to 0, factor out a 4x. Okay, this gives us x equals 0. That gives us actually imaginary numbers. We don't deal with imaginary numbers, obviously, with the first derivative test, so we're not, or with any derivatives or local max or min, we're not dealing with any imaginaries, so we're not going to deal with these. Anyways, x equals 0 is the only candidate we have, okay? And so with x equals 0, now what we're going to do, instead of making a sign chart, we're going to try the second derivative test. Okay, so we have the first derivative, we found a critical point, aka that was the first step here, find something where it's equal to 0. Then find the second derivative, so from here, that would be 12x squared plus 8. Okay, and we're not setting this to 0, we're actually just going to take whatever our candidate was and try plugging it in. So what's f double prime of 0? F double prime of 0 would be 12 times 0 squared plus 8, which is positive. Okay, so think about what are the two things you figured out. F prime of 0 is 0, and f double prime of 0 is positive. Okay, so take a look. Where does that happen? That's right here. Okay, again, it would look something like this. Concave up, and it's that 0 slope at the bottom, so it must be a local min. Okay, this guarantees it, these two conditions. So let's actually try writing that out. Our justification would be something like, since these two conditions, so since f prime of 0 is 0, and f double prime of 0 is positive. Okay, you don't have to say this part, but if you want to, just for the sake of notes here, by the second derivative test, again, you don't have to say that part of the sentence. You do need to say this part. There is a local min at x equals 0. Okay, so most important things you need are those two conditions, and then obviously saying it's a local min. So that's how we'd use the second derivative test. Like I said, you could have also used, if there was no directions particularly using this, you could have used the first derivative test, which, just to remind you, I'll do it in pink over here. That would have been this step. Then you would have made this chart. And you would have said like negative infinity, 0, infinity. You would have tested out values, and you would have gotten negative, positive, and then you would have gotten these arrows. And you would have decided it's a min because f prime changes from negative to positive. So obviously that still would have worked, okay? Again, I just wanted to show you a different way. So let's look at one where it's not flexible, and actually you'd have to use the second derivative test. So take a look at number 2. Okay, number 2, we have to use the second derivative test because there's no way for us to make a sign chart. This is the first derivative already, right? That's what this means. So dy dx, here's the derivative. Okay, we have to use second deriv test. The reason for that is if I said like make a sign chart, like how would you set this to 0? Well, you have x and y, okay, you have these variables mixed up. We have no way to make a sign chart here. All right, so let's work on answering these questions. Again, we're going to use that second derivative test for local extrema. So first it just says, determine if 1, negative 2 is a critical point for this function. Okay, well, you know something's a critical point if the derivative is equal to 0 or does not exist. So let's try this out. dy dx at 1, negative 2 would be 2 times 1 plus negative 2. Again, I'm just plugging into 2x plus y. Plugging in x and y. I get 0. So your answer would be, yes, it's a critical point because the derivative at 1, negative 2 is 0. Okay, so that's it for the first one. It was just asking, is it a critical point? Okay, part B is now doing, now that we know that the first derivative is 0, we can use the second derivative test to figure out, is it a local min or max? All right, so again, I wrote it up here. You have to use a second derivative. Okay, we can't use first deriv test here because we can't make sign chart with multiple variables, right? We have x and we have y in our first derivative. It's that implicit look. So we're just going to use the second derivative because we do know how to take the second derivative of this. All right, so how do we do that? Well, implicit, if you guys remember, we're going to take the derivative of both sides. This stands for the second derivative. Okay, what's the derivative of 2x plus y with respect to x? All right, well, that would be 2 dx dx, aka 2, right? X is act normal, okay, plus y, derivative of y would be 1 dy dx. Okay, so the second derivative is 2 plus dy dx. That's from implicit. Obviously, dy dx doesn't really mean much this way, so we are going to replace it with 2x plus y. So we're just going to substitute in. The second derivative is the same thing as 2 plus 2x plus y, right? Because that's just replacing dy dx. All right, so there's our second derivative. And again, what do we want to check? We want to know if the second derivative, okay, at this point, 1, negative 2, is it positive or negative? So let's plug it in. 2 plus 2x plus y. That would be 2, which is positive. That's all we don't even care that it's 2, but we care that it's positive. So you have 0, okay, as your first derivative. That was the first condition. You have the second derivative is positive. Again, that's concave up. You have 0. Again, that guarantees a local min. And look up at that top of our notes if you need help on that. Okay, so since dy dx at 1, negative 2 is 0, that's if the first derivative is 0, and the second derivative at 1, negative 2 is positive, okay, by the second derivative test. Again, you don't really need that part of the sentence, just I'm putting that in for the sake of the problem. There is a local min at 1, negative 2. Okay, so again, matching up, first derivative is equal to 0, second derivative is positive. That guarantees a local min, those two conditions. All right, so we're going to save number 3 for class, but let me know if you have any questions, and thanks so much for watching.